Thanks. So yeah, I'm Erin Teich at University of Michigan, and I'm going to talk today about a project that I've been doing for the past year or so with my advisor, Sharon Glotzer, and the newly minted professor of physics at Michigan, Greg Van Anders, on hard particle glasses and how we think that identity confusion in the structure of these systems leads to its glassy behavior. So just to set the scene ever so briefly, glass is a material that's been used by humans for literally millennia, right, for a variety of tools. So this is a photo of a cup made of glass that people think is from around the 4th century in the Roman Empire. And if you skip ahead, this is a very brief overview, if you skip ahead thousands of years, increasingly people are starting to use glass phenomena in technology. So people exploit the phase change behavior of certain materials from glassy states to crystalline solid states. And they use that as some underlying physics in rewritable optical disc technology, so like rewritable DVDs, for example. And to conclude our brief survey, experimentalists recently who study colloids, so these are particles on the microscale, have also observed glassy dynamics in their systems. And so the physics of glass is incredibly relevant throughout history and in a variety of fields. Despite this, however, Philip Anderson, who won a Nobel Prize in physics in 1977, once said, the deepest and most interesting unsolved problem in solid-state theory is probably the theory of the nature of glass and the glass transition. He said that in 1995, but most people think that it's still true over 20 years later. So physicists really still have yet to have a fundamental or canonical grasp on the true physics of the nature of glass. One of the reasons that is can be summed up in a plot that looks something like this. So these are different glass-forming systems, and this plot shows both their viscosity on this left axis here. This is an interesting angle. And their structural relaxation time on this right axis. And it plots that as a function of either the temperature for thermal systems or the density of the system for athermal systems. And what you can observe is that timescales for relaxation are increasing by orders of magnitude as the system approaches either its glass transition temperature, Tg, or its glass transition density, phi g. So the system is slowing way, way down, and it's doing so incredibly rapidly. Even the definition of the glass transition itself is phenomenological. So people don't even have a fundamental canonical description of what it means to be a glass. So people typically say that something reaches a glassy state when its time scale for relaxation is something like 14 orders of magnitude above its fluid value. So when things are slowing down this quickly, it becomes really difficult for physicists to get good statistics on the system. It becomes difficult to even make measurements either in a simulation or in an experiment. And so that's the source of some of this confusion. And so outstanding questions still remain about this material. One outstanding question that we were especially interested in is how system structure, and that a lot of people are interested in, is how system structure gives rise to this glass transition. So what's the relationship between the structure of the system and this dynamical signature that we can observe for all these different models? And so when people want to answer that type of question, typically they want a model that's very simple that can isolate the relationship between system structure and vitrification, which just means glass formation. We think, that coloring. We think that one example of a simple model that we are using for our study is something called a shape landscape, or we call it a shape landscape, and it can kind of be summarized by this graphic. So this is actually quite a bit of information to parse. But essentially, every one of these tiny grid squares represents a slightly different particle shape that we use in our simulations. And then the squares are colored by the structure that one component systems of these corresponding particle shapes actually assemble into. The particle shapes themselves are interrelated. So for this particular shape landscape, you can get from any particle shape to any other by a series of truncations. So for example, if you start with a tetrahedral particle shape in the corner here, if you truncate its vertices, so you just shave the vertices, you can continuously transform to an octahedral particle shape. But if you shave off its edges here, you can transform to a cubic particle shape continuously. And these are just representative, or these are just example particle shapes, but every one of these grid squares is a slightly different shape. The simulations that we actually do with these particles are hard particle Monte Carlo simulations. So that's actually a really simple technique. It just means that if we have a simulation of particles of some shape, we choose one randomly, or we choose a set randomly, and we make a random move of these, and we accept the move if it results in 0 overlaps in the whole system, but we reject the move if it results in any overlaps. And when you do such a simple type of system, actually you're getting at behavior that's going to be exclusively entropically mediated because there are no energetic interactions between any of the particles, so there's no potential energy in the system. And so when it wants to minimize its free energy, in this case the Helmholtz free energy, all it can do is maximize its entropy. And so this is kind of a pure physical model that we think is a good one. So for example, if you choose a particle shape in this pink region here, it self-assembles into the diamond structure. C stands for carbon in this legend. Whereas if you choose a shape from this orangish region, it's going to assemble into the face-centered cubic lattice. But in this giant gray area here, we found that we couldn't ever assemble an ordered structure at any density that we tried. So the system remained disordered. And so in this landscape, essentially, very small changes to the system, so very small modifications to particle shape, can actually toggle us between an ordered structure, a self-assembled ordered structure, and a disordered structure here. So this is kind of an ideal vehicle through which we can ask the question of how system structural differences that are perhaps mediated by or affected by small changes to particle shape might lead to vitrification or glass formation rather than assembly. So that's the question that we want to answer in this model system. In order to answer that question, we chose to kind of attack this on 2 fronts. First, we wanted to actually verify that these disordered systems were in fact glass formers. So we chose 2 different points in this shape landscape corresponding to these 2 different shapes. And we quantified the dynamical behavior of these systems and verified that they were glass-forming systems. And then we identified structural motifs that we think contribute to this glassy behavior. And I'm going to focus especially on point number 1, actually, because that's how we used, because we used blue waters to help us do that. And blue waters is very helpful in helping us do that. The simulation method that we used was this software toolkit HumDBlue that was developed by a research scientist in our group, Josh Anderson. It's totally open source. You can download it at this URL here. And it does both molecular dynamics and hard particle Monte Carlo, which is the method I was previously describing. It's especially well designed to take advantage of the resources on blue waters because it was designed to be quite parallel and it scales well to thousands of CPUs and GPUs. And it does this by taking advantage of spatial domain decomposition if you're using a GPU on a variety of length scales. So if you use more than one CPU or GPU, HUMD divides up your simulation domain into subdomains, separated by this little gray ghost layer here, and it performs the simulation in parallel on those domains. And if you use a GPU, then it actually further subdivides these subdomains into sub-subdomains in this checkerboard pattern here. So basically, it divides up the subdomain into sets of cells that are all colored the same. And then it runs a GPU kernel that basically chooses a set of cells at random and devotes a thread to each cell in the active set, and then runs the Monte Carlo simulation in parallel in each of those cells. So now I want to focus on how we use HUMD to quantify the behavior of these hard particle systems. I'm going to focus on two order parameters that we used to do this verification. The one to the left is maybe familiar to most people. It's just the mean squared displacement of the system over time. So this is just a sum over all particles in the system. So it's like the average per particle displacement over time. And these brackets are ensemble averages. And then this quantity to the right is maybe less familiar to most people. And it's called the self part of the intermediate scattering function. And you can think of this as basically just a Fourier transform of the displacement of the system over time. So it says something like, if I were to shine light of a certain wave vector k on my system, and I were to look at its configuration at time t with respect to its configuration at time 0, what kind of scattered intensity would I get back? So it's kind of a measure of the correlation of the system at time t with respect to its structure at time 0. And the great thing about both of these order parameters is that they indicate glass forming behavior by having plateaus at short times. So both the mean squared displacement and the self-intermediate scattering function level off at short to intermediate times. And this is indicative of a phenomenon in cages known as, in glasses known as caging, which is where, on average, every particle is basically trapped by a cage of its neighbors. So it doesn't really go anywhere. So this is kind of flattens out here. And only at longer times does the system actually structurally relax, and the particles on average are able to escape their cages, and the system becomes diffusive. And so this plateau behavior, this caging behavior, is basically a hallmark of glass forming behavior in these systems. So when we ran our simulations, I should say also, we'd actually just used one GPU per simulation on Blue Waters because we decided that was the most efficient use of our allocation. But it was still very parallel because of HUMD's parallelization. When we used HUMD to do these simulations, we saw this caging behavior in our kind of sample state points. So here the curves are becoming more, or they are more blue as the system density increases. And so you can see that this caging becomes more and more prominent as the system density increases. So this is verifying somewhat the glassy nature of our hard particle model. And this is also the case for the other particle shape that we studied. Although it's worth noting here that the caging behavior is weaker than in the previous state point, but it still exists. I want to acknowledge that when we were making these plots, we were making measurements on timescales that are varying by about 6 orders of magnitude. So this is that's quite a bit for us. And to get good statistics, we were taking ensemble averages for every trajectory over 10 independent time windows within each trajectory. And so together, that meant that every one of these curves basically represents a trajectory that we had to store on Blue Waters that had 100 million simulation frames that we dumped every 10 Monte Carlo sweeps. So for us, that's actually an enormous amount of data. It's very fine-grained in terms of its detail. And so we were producing something like 3¼ terabytes per file. But thanks to this allocation that we had on Blue Waters and Blue Waters' storage capabilities, that was kind of no problem for us. So we were able to just store it and then do this post-processing analysis without having to worry about where to put the data or how to access it or anything like that. So that was a boon to us for sure. So in the time I have left, I want to just discuss how we think that structure is driving this Glassy behavior in one example state point. So here we have a particle shape that we previously have verified the Glassy behavior of. This is a disordered snapshot of that system. And when we look at structural motifs in the system, particularly very local structural motifs, so if you just look at pairwise configurations of particles in the system, what we found was that there are two main competing motifs in this system that emerge. And hopefully you can see the difference somewhat. These are basically two particles that are bonded face-to-face with each other. But the difference is that in one motif, there's a twist in one particle with respect to the other. So it's a really small difference, but a difference nevertheless. And if you look at nearby shapes in this shape landscape that do form ordered structures, you find that one motif or the other dominates in these ordered structures. So in a nearby point that forms diamond, you find the twisted motif dominating. And in a different nearby point that forms a dodecagonal quasicrystal, actually, which is a very fascinating structure in its own right, the non-twisted motif dominates. And so what we can say for this particular disordered system is that there are competing motifs here, technically in shape space, that are giving rise to an amorphous network of tetrahedrally coordinated particles. So every particle is wanting to be face-to-face with its neighbors. So it has neighbors that are tetrahedrally coordinated, but it's forming a network that's disordered rather than an ordered structure. And in fact, that's behavior that's seen all the time in network glasses. So things like silica glasses or some models of amorphous ice. And so we were really heartened to see this and to see that using this really simple model, we were actually accessing some deep physics that parallels physics of other slightly more complicated models. So I just want to conclude and say that this model, we're excited about it. It was enabled by resources that we had on Blue Waters, and it allows us to kind of have this hypothesis that for this system, identity confusion in shape space is giving rise to competing local environments, competing structural motifs, and consequent glassy dynamics. So with that, I just want to thank, again, my collaborators on this. And I also especially want to thank the Blue Waters Graduate Fellowship for their support and their allocation and really allowing me to dive pretty deeply into this project over the course of the year. So thanks.